Hello everyone, my name is Alexander Kazantsev, and today I'd like to introduce you to my design. Let's start off with the introduction. So, the device that we propose is an autonomous acoustic synthesizer. I'll provide a demo later for what this looks like. Currently in the market, there are no major competitors that design autonomous acoustic synthesizers that operate on a linear track. We propose a stringed instrument that operates over a MIDI interface to solve this problem. So we would like to deliver an instrument that generates sound acoustically. A cart is placed on each string to fret the string, and the string is actuated by a guitar pick. The user will operate the system through a MIDI interface. So we did some research first. A research effort was comprised to identify products in the market that are within this scope. Some of these products are computer-based synthesizers, which synthesize music digitally, autonomous player pianos, and autonomous but not acoustic synthesizers, which can be analog electronic synthesizers and computer-based synthesizers. The player piano does synthesize acoustic music without human intervention, but it does not operate on a linear track, which is what our product proposes. The base requirements of our system are an instrument that can autonomously pluck and fret a string. The acoustic effect of this will be similar to that of a slide guitar, so it will sound like someone using a slide on a guitar to fret their string. There are physical limitations that must be overcome for a system like this to work in real time. The maximum amount of time that it should take to reach a certain note should not exceed 1 second. There also needs to be granularity in position feedback, 8 millimeters in our case, which is the distance traveled over one motor rotation. These numbers were determined heuristically. So the protocol that's going to be used between the user and the system is MIDI, and that's going to be the middleman between the user and the system. MIDI was chosen as it is a standard across many electronic instruments, and because of this, our system will be interoperable with many electronic musical devices. This is a simple block diagram for the general layout of a system. The user specifies a set of playable notes on the MIDI device. Then the controller parses the MIDI output and translates that to a string pluck and position of the fretting cart on the track. The string will resonate over a guitar pickup, which is fed into an amplifier that will output our acoustic signal. Here's a simple drawing of the system to help visualize it. So here in the center we have our lead screw, which is rotated by our motor over here on the right. The motor's here on the right, and the fretting cart is what provides a certain fret provides tension on the string, and that's moved on a linear track by this lead screw. This is an operational diagram for our software-defined system. When turned on, the system will first initialize, which will include zeroing the fretting cart for an initial position. Next, the system waits for user input through MIDI. When input is received, the appropriate string will immediately be plucked, and the fretting cart will be sent on its way to the desired position. The system will stay in the input pluck and set point state indefinitely until turned off. So when designing the electronics for this device, we must adhere to some standards and regulations. Some of these include UL 1310, which is a safety class for power supplies, IEEE 11490-49.1, which is JTAG for programming microcontrollers, and lastly, like I mentioned before, MIDI, which is a standard protocol between our system and any electronic musical device. So budget. In our industrial budget, we've included the cost of engineers, space required to build the prototype. Everything is prorated to 9 months, as this is the length of our project for senior design. For choosing the engineer cost, this is a statistically average cost for engineers on the East Coast. And then some company benefits were included, and this was prorated over 9 months. So over a year, it's $370,000, but prorated it's $277,000. And to our right, we have the funding required for space to actually build our device. So the cost of items required to build the prototype are included. Licenses for software, test equipment, and build equipment are all part of this cost. The sum total, including our engineering costs and space costs, ends up being right around $350,000 over the span of 9 months. So here we have our current progress on our system. This is the picture present in this slide is our first rough prototype of what a single string implementation may look like. What is visualized here is the linear track with the fretting card attached that is driven by the motor. The motor rotates the lead screw, which moves the fretting card back and forth on the linear track. The fretting card is the little red pillar you see in the photo. The motor is off to the left, which is attached to our lead screw, and that it moves it back and forth. So next, to effectively design control algorithms for a given device, the physical system had to be mathematically modeled to fully scope our proper controls. Figure 7 shows a schematic that looks like a circuit, which is actually the physical system modeled as an electric circuit. The reason for this is that it allows us to easily model our system with a set of differential equations, which are present in our state space matrix in Figure 8. This is similar to how simulation software such as PSpice models circuits in software. Lastly, we have our timeline. Our timeline, again, is prorated to 9 months. This is a Gantt chart used to show the timeline of our design work that has been done, so that needs to be done. Most of our time will be spent on constructing the physical system, designing control algorithms around the model, and testing the system. So that's a basic summary of our system, and I hope you enjoyed my presentation. Thanks.